Please note that filming text on a whiteboard requires extremely bright studio lighting. Subsequently, sunglasses were worn during the filming of this video to prevent damage to my retinas. A note on how to use these sessions. Jot down the notes as we go, so we'll help you learn the material in a more interactive way and you can use them as study notes later. Also, in the small chance that a discrepancy arises between the professor's notes and mine, always go with your professor. They're the one grading you. Lastly, any examples or analogies used in this session are not meant to support or criticize politics, religion, or lifestyle. They're merely learning tools to help understand the material. Alright, guys and girls. It's time to get cracking.
Alright you guys, today we're going to be talking about IR spec, infrared spectrometry. But first things first, because I'm sure you've been hearing things like IR, NMR, and mass spec. What are these things? Well, these three things are just techniques that we use in the lab to analyze the compounds that we make. Okay, so you do an experiment in the lab, you mix all these chemicals together to try to make a certain compound. Then after you make that compound, you want to say, hey, did I make the right compound or not? You want to test what it is. Okay, so we have three ways of testing what our compound is. And what are they? Well, we've got NMR, IR, and mass spec. Let's write this down. Okay, so these are our three analysis techniques. We've got NMR, IR, and mass spec. So like I was telling you, we basically do a reaction in a flask. We pour a bunch of stuff in here, right? And we mix all of this together. We're hoping to make a certain compound. After we mix all of these together, then we want to see if we made the right compound. So we take a little sample of this and we put it into an NMR machine, an IR machine, and also a mass spec machine. And each one of these is going to tell us different information about this compound that we just made. Okay, so let's find out what type of information we find out from each of these analysis techniques. Alright, so this first one that we have is NMR. Does anybody know what this stands for? Well, this stands for nuclear magnetic resonance. And you can write that down, but the name isn't telling us too much. All this is saying is that nuclear magnetic resonance, nuclear, it's analyzing the electrons in the nucleus of your compound. Magnetic, it uses a magnet to do this analysis, okay? But we're going to find out all about that later. All I want you guys to understand right now is, in general, what each one of these does, or what we use it for, okay? So, does anybody know what we use NMR for? What we use it to check for? We use it to check for a compound's connectivity, its structure, how a compound is put together, okay? So, hey, let's write this down. Okay, so NMR, this is used to check for a compound's connectivity, its structure, how a compound is put together. So very, very important information from an NMR. An IR, on the other hand, doesn't tell us anything about a compound's connectivity. Does anybody know what an IR will tell you? Well, we use an IR to check for functional groups in a compound, whether or not your compound has an alcohol, a ketone, an aldehyde. All those functional groups you guys learned the names of in first quarter ochem, this checks to see if your compound has any of those. Okay, so let's write this down. That IR, infrared spectroscopy, this is used to check for a compound's, not connectivity, but functional groups. Okay? So an IR tells you nothing about how the compound is put together, but it will tell you if you have certain functional groups, an alcohol, a ketone, an aldehyde, an ether, all those good stuff, okay? Alright, so last but not least, we have mass spectrometry. Does anybody know what we use mass spec to check for in a compound? Well, we use a mass spec to check for a compound's weight. Okay, so this is just like a giant scale for a compound. So if you take me, I step onto a scale, the scale reads out, you weigh 150 pounds. This is the same thing for a mass spec. You take your compound, stick it into a mass spec, and then the mass spec reads out, this compound weighs 150 grams per mole or whatever it is, okay? But this is really important because, hey, say you're in the lab, you're making a compound, you know exactly how much that compound is supposed to weigh. So when you take this and you put it into the mass spec better read out the same weight that you were expecting, otherwise you didn't make the right compound, right? Just like if you took me, put me on a scale, I better read 150 pounds. If it read 75 pounds, then that means I'm not on the scale, right? It's somebody else that's on the scale, okay? So let's go and write this down. That mass spec, this is used to check for a compound's molecular weight. All right, so let's see a quick example of how this works. Okay, so say you're down in the lab and you're mixing a bunch of stuff together in this flask, right? And you're trying to make this compound, a C double bonded to an O, with a CH3 on both sides of it. Okay, so this guy's molecular formula would be C3H6O. Okay, so molecular formula C3H6O. This is what you're trying to make. So you mix all the stuff together, you think that you made this, but you want to be sure that you made this, right? So how can we check to make sure that we made this exact compound? We'll take a sample of this and stick it into an NMR, an IR, and a mass spec, and this is going to give us information about this compound's connectivity, functional groups, and its weight. Okay, so hey, from its molecular formula, we know how much this thing should weigh, right? So how much should this weigh? Well, what you can do is break it down by the atoms. So hey, we've got three carbons. So a carbon weighs, if you look at the periodic table, it's going to weigh about 12 grams per mole. We've got 3 of them. So this is going to be 36. Hydrogen, we've got 6 of them. So hydrogen, it weighs what? About 1 gram per mole, right? So 1 times 6 of them, that's going to give us 6. And oxygen, if you look at the periodic table, well, we've got 1 of them here. So oxygen's molecular weight's what? It's about 16. We've only got 1 of them, so this is going to be 16. So hey, 16 plus 6, that's 22 plus 36. This thing should weigh about 58 grams per mole. So what you're going to do is take a sample of this, stick it onto the mass spec, and it's going to read out, your compound weighs 58 grams per mole, hopefully. If it reads out that your compound weighs like 100 grams per mole, then you did something wrong. You didn't make this compound. So hey, you take a sample of this, put it into the mass spec, hopefully it reads out, your compound weighs 58 grams per mole, which is what you were expecting, okay? All right, so we stuck this thing into a mass spec, made sure that this thing weighed what we were expecting it to weigh. Then we can look at the IR to check for functional groups. What kind of functional group would you consider this? Where you have a carbonyl surrounded by 2 alkyl groups? This is a ketone, right, you guys? So you better see in your IR spec that a ketone is present in this compound. If you don't see a ketone in the IR, that means something went wrong with your experiment. You did not make this compound, okay? And the last thing you can check is NMR, which is the compound structure, how this thing is put together, okay? NMR, you're going to find out all this big time in the next chapter. But for now, all I want you guys to understand that an NMR will help you find the compound's structure, how this thing is connected together. An IR is going to tell you, hey, you have a ketone or not. A mass spec is going to tell you, hey, how much does your compound weigh, okay? All right, so now let's talk about IR, infrared spectroscopy, in detail now. And if you haven't already, go ahead and print out a copy of the 2 IR sheets that I gave you, along with the sheet of IR absorption. It's the one with all the peaks that I've drawn on it, okay? Because we want to refer to this in today's session. First thing I want to do though is start out with a general strategy for how you look at IRs, because you look at IRs completely differently than you would an NMR. Okay, so an NMR, this is going to have very few peaks on it, and you want to look at all of those peaks, okay? In comparison to an IR that we're looking at today. IRs have a ton of peaks on them, and you only want to look at a few of those peaks. Okay, so let's say that one more time. An NMR has very few peaks to start with, and you want to look at all of them, in comparison to an IR that has a ton of peaks, and you only want to look at a few of them. Okay, so hey, have any of you guys played those Where's Waldo books? Yeah? Okay, so what's the goal of Where's Waldo books? To try to find Waldo, right? And in those books, you've got 10 million things that are trying to distract you. Like they have an alligator, a shoe, a horse, whatever it is. You've got a bunch of different things on that page that's trying to distract you from finding Waldo. And do you spend your time looking at all of those things that are trying to distract you, or do you just try to go right to Waldo? You want to go right to Waldo, right? And it's the same thing on these IRs. An IR has 10 million peaks on it that's trying to distract, not really 10 million, but it has a lot of peaks on there that are trying to distract you from the important peaks. And that's what usually screws people up, because they look at these IRs and they say, oh my gosh, look at all these peaks. What does this peak mean? What does this peak mean? But no, you guys. You screen out all the unimportant peaks and you just look for Waldo. You just look for the peaks that are important, okay? All right, so now you know the strategy for how to look at an IR. An IR has a ton of peaks on it. You want to ignore most of them and just focus in on the few important peaks. But hey, what makes a peak important? Why is one peak more important than another? Well, what's the goal of an IR? An IR is used to check for a compound's functional groups, right? It's used to check whether or not you have an alcohol, an ether, a aldehyde, a ketone, whatever, right? So an important peak in an IR is one that indicates that you have one of those functional groups, okay? So each functional group you have, like an alcohol, an aldehyde, ketone, each one of those has a characteristic peak in an IR, and those are the ones that you're looking for, okay? So let me show you an example of what I'm talking about. So say, for example, you just did a reaction and you were trying to make this compound. And what type of functional group does this compound have? It has an alcohol, right? So hey, you make this, or you tried to make this, you want to test to make sure that you made this compound. What can you do? Throw it in an NMR, IR, or mass spec. Today we're focusing on IR, right? So let's take this thing, throw it into an IR, and the IR is going to tell us whether or not we have an alcohol functional group, right? But your IR is not just going to say, yes, this compound has an alcohol functional group. It's going to print out something that looks like this. Okay, so it's going to print out a piece of paper. This is an IR spec. It's going to be labeled from 0 to about 5,000 or so, and it's going to have a bunch of peaks on it. Okay, so let's say, for example, there's this big broad peak around 3,400. You have these other peaks all along this IR, okay? I'm telling you that in an IR, it has a ton of peaks, most of which you want to ignore. And only a few, maybe only one important peak that you want to focus in on, okay? So this big broad peak around 3,400, this is an important peak. It's indicative of you having an alcohol in your compound. Okay, so if you ever see a big broad peak like this around 3,400, you should be thinking, hey, my compound has an alcohol in it. Okay, so I'm telling you that each functional group, for example, this is an alcohol, an OH, each functional group will have its own characteristic peak at its own characteristic location. And alcohol has a big broad peak at around 3,400. Say, for example, that this compound, it also had an ether in it. So let's say there was an ether functional group in this compound. Then we would have also seen an important peak at around 1,100. So we would have seen an important peak at 3,400 for the alcohol, and we'll also see an important peak at around 1,100 for the ether. Okay, so the whole idea here is that you're going to get a ton of peaks in your IR. You want to ignore most of those and just focus in on the areas that are important. Okay, so an alcohol is at around 3,400, and ether is at around 1,100, and each functional group will show up at different places on this IR, and those are the places that you want to look. You want to ignore everywhere else and just focus in on the important places. Okay, but hey, how do you know where these important places are? Well, that's where this sheet of IR absorptions I gave you comes in. Okay, so IR absorption, same thing as peaks. This sheet outlines for you what all of the peaks for each different functional group looks like and where it's going to show up on the IR, okay? All right, so on this IR absorption sheet, these are the peaks that you're looking for. These are the important ones that represent the different functional groups. And I know it looks like, oh my gosh, we've got 1, 2, 3, 4, 5, 6, 11 different peaks here. Am I supposed to memorize all of these? And yeah, you guys, you want to try your best to memorize all these different peaks. You want to be able to say, okay, I expect an alcohol to appear at around 3,400. I expect an alkene peak to be around 1,650. I expect an ether to be around 1,100. And hey, what do you also notice about these peaks?